All right, let's jump right in. What if a problem that the absolute brightest minds in mathematics called impossible for 200 years? Well, what if it wasn't impossible at all? We're about to dive into a story that really challenges a core truth of algebra, something that's been set in stone since 1824. And it all kicks off with one simple question.
Seriously, think about that for a second. When we label something as impossible, are we really stating a universal fact? Or are we just, admitting the limits of our own tools, our own imagination? For 2 entire centuries, a whole class of math problems has been locked away in that impossible box. But now, we're going to look at a claim that says someone just picked the lock.
So our story really begins with a quest that's as old as algebra itself, the hunt for x. For hundreds of years, solving these polynomial equations, finding that one perfect, exact answer was kind of the benchmark for our mathematical progress. It was like climbing a mountain of ever-increasing complexity, one step at a time.
And you know what? For a long time, that climb was going great. Ancient mathematicians totally nailed second-degree equations. Then, in the 16th century, we got these huge breakthroughs for the 3rd and 4th degrees. We were on a roll. But then, in 1824, the path, it just stopped. Progress slammed right into a wall. Equations of the 5th degree and higher were officially, formally, declared unsolvable.
Now, this wasn't just some gut feeling. It was a mathematical proof. It created what you can basically think of as Abel's wall, a giant barrier of impossibility. And for 200 years, this theorem has been a foundational truth, something taught in every university as the absolute limit of what algebra can achieve. That theorem is called the Abel-Ruffini theorem, and it's super specific. It says there's no general formula for these tougher equations if, and this is the key part, if you're only using the standard tools of algebra. Adding, subtracting, multiplying, dividing, and using radicals, which is just the fancy word for things like square roots, cube roots, and so on. For 2 centuries, that was the final word on the subject. Period.
So why did everything grind to a halt? Well, imagine trying to untangle a really, really messy knot. As the equations got more complex, the number of moving parts just exploded. The old algebraic tools were like trying to solve a tiny, intricate puzzle while wearing big, clumsy mittens. It was just too much. So mathematicians had to give up on finding that perfect, elegant answer and just settle for getting close, using numerical approximations. But, as we all know, limits are often just waiting to be challenged. And this is where Professor Mourad Sultan Ezouidi enters the story. He's a mathematician who looked at this 200-year-old wall of impossibility and didn't see an endpoint. He saw a challenge.
And his whole perspective is captured in this simple but incredibly powerful statement, but I have never accepted that limitation. That's not just being stubborn. It's a deep belief that the problem wasn't with the equations themselves, but with the tools everyone was trying to use. It's a direct challenge to 2 centuries of mathematical certainty.
And his claim? It's absolutely monumental. He says he's developed a method to find the complete, exact, symbolic solution for a 7th-degree polynomial, something the Abel-Ruffini theorem said could never, ever be done. And we're not talking about an approximation here. We're talking about pure, perfect algebraic precision.
So the big question is, how is that even possible? Well, the key wasn't to just get better with the old tools, it was to invent a completely new toolkit. And to really get what's going on, we need to compare his new idea, Ezouidi's theorem, with the classical way of doing things. This table really shows just how big of a shift this is. Classical methods straight up said, impossible. You have to settle for approximations. Ezouidi's method, though, it's built on a totally different idea, something called recursive structures. Think of it like a set of Russian nesting dolls. It finds a way to break the big, complex problem down into simpler, nested versions of itself. This allows for 100% verifiable, exact answers. It's a total change in philosophy from it can't be done to, hey, every equation has a perfect answer just waiting to be found. So here's the core idea in 3 steps. First, the method just completely sidesteps the old rules that led to that impossible conclusion in the first place. It's like finding a whole new path around the wall. Second, it transforms the equation. Imagine taking a really complex machine and cleverly reorganizing its parts into smaller, simpler machines that fit inside each other. That's kind of what these recursive transformations do. And finally, once it's all reorganized, the equation's own structure just reveals the exact answer. It's almost as if the polynomial is coaxed into solving itself.
And this brings us to what might be the most important point of all. This breakthrough isn't just about getting an answer. It's about the kind of answer we get.
It forces us to ask what we even mean when we say we solve an equation. I mean, is close enough really a solution?
This image says everything. For centuries, the best we could do was the stuff on the left. A messy, endless decimal that's always close but never, ever perfect. This new claim is like the result on the right. A single, perfect bullseye. It's the difference between writing down a number that goes on forever and just simply writing the square root of 2. It's the difference between an estimate and the truth.
For 200 years, that messy approximation was the only game in town. It was an accepted compromise. This new work claims to throw that entire compromise right out the window, replacing all that estimation with pure certainty and precision.
So, let's say this claim holds up. It passes the intense scrutiny of the math community. What changes? This is so much bigger than just one equation. It's about what else suddenly becomes solvable. This could honestly be the dawn of a whole new era in mathematics. And what's really fascinating is that this new perspective doesn't say Abel was wrong. It actually says he was right, but only within the very specific limits of the 19th century toolkit he was using. His theorem drew a perfect boundary around one set of tools, but it couldn't draw a boundary around mathematics itself. And that just blows the doors open for the future. What if every single polynomial, no matter how ridiculously complex, actually contains the blueprint for its own perfect solution locked deep inside? The whole mindset shifts from, we can't solve that, to, we just haven't found the right key yet.
And that leaves us with one last big idea to chew on. If a mathematical truth that stood firm for 2 centuries could be upended by a new perspective and a new set of tools, what other scientific impossibilities are we just accepting today? What other long-standing limits are really just historical misconceptions waiting for their own challenger to come along and give them a push? What other walls are just waiting to fall?